Good afternoon, and thank you for joining us for the Risk-Based Safety Planning for Tribes webinar. My name is Jamie Sullivan. I'm the Director for the National Center for Rural Road Safety, and we are co-hosting today's webinar with the FHWA, Office of Tribal Transportation, and the NLTAPA Safety Working Group. Before we get started, we just have a few logistics for you all. Our webinar today is going to be an hour and a half long. Closed captioning is available and has been emailed out and is available in the chat pod currently. We will be recording today's webinar, and that will be available within the next couple days on our website at ruralsafetycenter.org/webinar-archive. We do have a question and answer pod over on the right-hand side. Please feel free to put your questions in there at any time, and at the very end of today's presentations, I will be asking those questions out loud to our presenters. Handouts are available for download. You can see over on the right-hand side of your screen that those are available already as PDF versions for everybody's presentations today. At the end of the webinar, we also will provide you with a feedback form to provide us with additional information on the webinars that the center hosts and what additional topics you may want to see. And lastly, we will have certificates of completion and an application for CEUs available for today's webinar. Those will be provided to you by email in about 3 to 4 weeks. I do want to also remind you that the Tribal Transportation Safety Fund is open currently, and applications are being accepted until January 15th. And the link can be found on the slide, which is also available as a handout. And I will put this link into the chat pod when I hand this webinar over. Our agenda today, we have quite a few speakers and topics for you all. Our very first speaker is going to talk about an introduction to risk-based safety planning. We'll then have an overview of the ABLI Safe Curves pilot. Then we'll be hearing from a speaker about using 3D data to identify safety concerns. We'll then hear an overview of the US RAP program, and then lastly, we'll hear a case study about the US RAP program and some of the tribal pilots using 360 cameras. As I mentioned, we do have several different speakers for you today. So we are going to be starting with Adam Larson, who is the Safety Engineer and Safety Program Manager for the FHWA Office of Tribal Transportation. Then we'll hear from Steve Abley, Larry Moore, Zachary Hand, Kim Vachel, Ron Hall, and Sherijad Hassan. And so for Adam Larson, he is the Safety Engineer and Safety Program Manager for the FHWA Office of Tribal Transportation. He provides transportation safety technical assistance to tribal governments and manages the Tribal Transportation Program Safety Fund at the Federal Highway Administration Office of Tribal Transportation. He joined that office as a civil engineer in 2011, and I'm excited to hand over today's presentation to him now.
All right, Jamie, can you verify you can see my screen?
Yes, we can.
Great, thank you. So I don't want to take a whole lot of time. I just want to give a little bit of background for today's discussion on risk-based safety planning. And today is the second of 2 webinars on the topic of risk-based safety planning in tribal areas. And so if you missed yesterday's webinar, there will be a recording of that available through the National Center for Rural Road Safety. We'll also distribute information through the tribalsafety.org mailing list on both the recording for today and from yesterday. I want to start this conversation just by talking briefly about data deserts. And in many tribal areas, we have a lack of crash data, and we'd like to have more data to be able to identify, prioritize, and justify safety improvements on the roadways. And for a variety of reasons, oftentimes that data is not available, especially crash data is often lacking in tribal areas. And the result of this is that traditional means of safety analysis can give a false appearance of safety. If people are looking at a map of crashes and there aren't very many crashes in the tribal area, that appears then that the tribal area is safer than some of the other areas. And the result is that resources often go other places. And when individuals do try to make improvements, it's difficult for them to justify those improvements because there is no data available. So there's a few strategies for addressing safety when you're in this data desert situation, starting with transportation safety plans. And many tribes at this point have a transportation safety plan. Some of those are getting to be somewhat dated, but they are a useful tool in at least starting the conversation around what needs to be improved to make transportation safety improvements. Oftentimes, those plans include a component of working toward improved, better data, and that's both crash data as well as other types of safety data like asset inventories. And we'll hear about how survey data can be used in safety assessments today as well. There's a variety of different things that can be used for safety data, but again, making improvements to those data collections over time is another way that we can help to fill in some of the data desert. And then finally, what we're going to focus on today is using risk-based models, risk-based strategies to perform safety analysis and identify, prioritize, and justify those safety improvements. The term risk-based safety analysis is also sometimes called the systemic safety analysis method. And so Federal Highway does have a guide called the Systemic Safety User Guide that was recently updated just a few months ago. And the point of the systemic method is basically that, especially in rural areas, oftentimes when you look at where crashes are happening, those locations tend to be random. They tend to appear random, at least. They tend to not be in one location, and it may not be the dead man's curve or the really bad intersection. Those types of places can come up, and certainly we want to address those when we can. But the systemic method gives us a way to look at not crash location so much, but to focus on what are the contributing factors in those crashes and what types of crashes are occurring, and how do we address those across the system rather than trying to focus on location. I do want to mention the safe system approach. I'm not going to go into detail on this. Hopefully you've heard of the safe system approach, and it is kind of the basis for everything that USDOT is doing for safety is being strategized around the idea of the safe system approach. But the most critical element for what we're going to talk about today is that safety needs to be proactive. And so these risk-based methods do help you to make those improvements, oftentimes in locations where the crash hasn't happened yet, but you have the right recipe. You have all the elements there that one day likely will cause that serious crash to occur. The timing of this discussion is no coincidence. As Jamie already mentioned, the 2025 Tribal Transportation Program Safety Fund is currently accepting applications until January 15th of 2025. And I don't want to go into a lot of detail, but again, that's available right now for you to apply for. And there are 4 different categories in the TTP Safety Fund. Most critical to talk about to our discussion today is the data assessment, improvement, and analysis category. And the examples that you're about to see are types of work that could be eligible as a data analysis project. And so each of these speakers will be sharing about their product that they offer, the type of analysis that they offer that is systemic safety related, as well as North Dakota State University is going to be talking about a project that they did with the road, or are currently doing with the Roadway Safety Foundation that is also a risk-based approach to safety. To keep myself out of hot water, I'll just say the U.S. government doesn't endorse any companies, products, methods, or manufacturers, but the types of methods that you're about to see are related to some of those methods that we do promote the systemic method specifically. So with that, I'll hand it back over to Jamie, and we'll get on with the show.
Perfect. Thank you so much, Adam. And our next speaker is going to be Steve Abley. Steve is a professional engineer, founder, and chief executive of Abley. The firm is a strong supporter of the Safe System approach and a trusted advisor to many governments and agencies of government. Abley extends its technical reach through the Abley Safe System suite of products, including Safe Curves, which will now be what we discuss.
Thanks very much, Jamie. Is that on screen?
It is. It looks great.
Thank you very much. Well, look, thanks very much, and hi everyone. I'm Steve Abley, and I'm very proud to be able to share a little bit about Abley today and Safe Curves. Given I speak a little bit different from the other presenters today, I thought I'd quickly share a little bit about me and Abley before delving deeper into our proactive, systemic and safe system approach aligned road safety tool named Safe Curves. First off, I'm coming to you today from New Zealand. This is Christchurch City, which is located on the east coast of the South Island, about an hour's drive from the Southern Alps that are shown here in the background. Today, I'm in my office, which is located about here. It's just after 10 o'clock in the morning, which I recognize is behind you, but it's also one day ahead. This is the Abley team. We're a group of multidisciplined professionals, and our firm is named Abley because I founded it some 20 years ago. Importantly though, we have world-leading experts in the area of road safety, and today we're undertaking commissions in New Zealand, Australia, Brunei, Indonesia, Canada, and the United States. The reason we're sought out for our expertise is because Australia and New Zealand have been working with the Safe System approach to road safety for about 2 decades. So we have real-world experience developing and applying tools that align with the Safe System way of thinking. Today I'm going to cover these 5 topics. At the end of my presentation, you'll understand how Safe Curves can be used to help with your grant applications to the Tribal Transportation Program Safety Fund. Okay, so let's start with why horizontal curves are important. Horizontal curves represent a change in direction for a motor vehicle. The problem is most rural curves have not been designed, and rather they've evolved over time, and at best they've simply been modified to allow for faster vehicles. Only on Monday, TRB issued its report titled Tackling the Road Safety Crisis, where they identified that only 20% of the US population lives in rural areas, yet 40% of traffic fatalities occur outside cities. That means that focusing on rural roads and diagnostically speaking, higher speed horizontal rural curves is especially prudent. So given rural curves are a focus area, and as a road safety professional, you need to answer 3 key questions when addressing horizontal curves. 1, where are these curves and which ones are high risk curves? 2, which curves, or better described groups of curves, are more important than others? And 3, what real-world countermeasures can be done to remove or minimize the risk of a rural roadway departure that will likely result in death or serious injury? Well, traditionally, Adams explained that safety issues with horizontal curves were detected by looking at crash data to identify black spots. This is particularly problematic on low volume roads where crashes tend to be more sporadic and more difficult to predict, often referred to as whack-a-mole. The systemic approach is championed by FHWA, and the example in the middle is a style of systemic analysis using reactive crash data. One of the easiest and most cost-effective countermeasures for horizontal curves is warning the driver of an impeding risk. That includes signs and assessing curve advisory speeds. The picture on the right is a digital side thrust indicator, and this, or alternatively an analog ball bank indicator, is one way to do that, but it is also pretty labor intensive, involving driving the curve multiple times in both directions. This then raises the question, is there a better way? And leads nicely into describing what is safe curves. Safe curves is different, yet still addresses those three important questions I raised earlier. Safe curves is proactive, systemic, and safe system approach aligned tool that accelerates the speed at which you can get to decisions. The safe curves data is accessed via a web portal shown here, and you can also be consumed into your or your consultant's GIS system, so you combine safe curves data with your other data sets. Safe curves has three modules. The first is identify, that identifies high risk curves. This is done for every curve and in both directions. The second is prioritize, that prioritize corridors for safety improvements. This aggregates individual curve risk into corridors so that you can provide corridor treatments that enable a consistent driver experience. And the third is interventions, that specifies MUTCD compliant signage, including the location, type, and grouping of curve signs, and it also provides curve advisory speed plaque recommendations. Now you're probably thinking, how does it do all that? Because that's a big ask. I'll start with the most important part first, and that's the individual curve risk. The key input is the approach speed that's influenced by the preceding geometry that the driver has just experienced. For example, acceleration on straights and deceleration on curves. If the approach speed is less than the maximum safe exit speed, the curve is within the context of the preceding road environment and it's a desirable curve. This is showing green and titled a class 3 curve. If the approach speed is more than the maximum safe exit speed, this is an undesirable curve and shown amber entitled a class 2 curve. If the approach speed is far greater than the maximum safe exit speed, this is an unacceptable curve and shown red entitled a class 1 curve. For both the class 1 and class 2 curves, the curve is out of context with the preceding geometric environment. These curves are far riskier than class 3 curves. But don't take my word for it. This is what happens when you take all of the fatal crashes in the US over the last 10 years and overlay them on top of all the curves in the US. There's a clear relationship that out of context curves are riskier than within context curves. This is the same relationship we've found in New Zealand and Australia, and it's unsurprising we've found the same relationship in the US, given our rural environments are all pretty similar. The important takeaway here is class 1 and class 2 curves have a demonstrated higher risk of a fatal crash, and that's where you want to prioritize your effort and resource. So let's now talk about the pilot program that we're undertaking with the 4 early adopter tribes. We're privileged to be working with Pueblo Jimenez, Hopi Reservation, Wind River, and Oglala Sioux tribes. The intent of the pilot program is Safe Curves data enables those tribes to develop a program for systemic roadway departure countermeasures. And importantly, because Safe Curves is a proactive, systemic, and safe system aligned tool, it also aligns with FHWA best practice when developing systemic roadway departure countermeasures. And I'll come back to that later. So let's walk through an example of how to use Safe Curves, and we'll use a simple example from Pueblo Jimenez. Okay, this is Safe Curves. What follows is a series of screenshots describing how the Safe Curves data is interrogated within the Safe Curves app. Because this is a series of screenshots to save on presentation bandwidth, try and imagine the cursor moving between each of the click points. What is shown on screen is a map of Pablo Jimenez. The three red boxes, identify, prioritize, and interventions, aligns with the questions I posed earlier and reflect each of the three modules within SafeCurves. I'm going to start with identify. That is, where are the curves and what is their safety risk? Down pops a box and you can turn on and off each of the curve classes. You can also show the fatal crashes as recorded in the NHTSA FARS database. I've turned on the class 1 curves and you can see a couple of red lines overlaying the road network. Next, I've turned on the class 2 curves, and just to remind you, together the class 1 and class 2 curves are outer context curves, and these curves are the ones that have a disproportionate crash risk compared to within context geometry. I've now turned on the class 3 curves. These curves are within context, and altogether the class 1, class 2, and class 3 curves represent all the curves. Here you can see I've selected one of the class 1 curves and a pop-up is displayed that tells me the curve details, including curve class, in this case curve class 1, its radii, its start and end position in decimal lat long, and the speed limit. This yellow icon provides a link that goes through to Google Street View. I'll select that now. And up pops a new browser window and it taking me directly to the curve being assessed. So if you need to, you can visually identify or verify the infrastructure on the curve. I'll return to the SafeCurves app and select the next module, Prioritize. What happens next is a drop-down box shows the different prioritization categories. It's at this stage that individual curve risk is combined with risk exposure, i.e. traffic flow, but all those calculations are done for you behind the scenes. What is important to note is that priority 1 is higher than priority 2, and so on and so on. We're particularly interested in priority 1 and priority 2 corridors that together only represent a quarter of the network length, but together they hold over half of the network risk. So if I click select all the network is shown and the curves have been aggregated into homogeneous driver experience corridors. These are then prioritized based on risk and exposure. If I select the corridor, a pop-up display is showing the priority number and location. Finally, the third model is interventions. The drop-down box shows the various MUTCD horizontal alignment sign categories along with the corresponding advisory speed if a curve advisory plaque is specified. Again, when I select all the signs are shown and the coloured border surrounding the sign reflects if the MUTCD specifies if the sign is required, i.e. red, recommended, it's amber, or optional, it's green. I've highlighted a location that shows a curve with 2 required signs in red, and I'm going to zoom into those signs now. This is a close-up of those signs, and you can see although there are 2 signs, they reflect more than one curve. That's because SafeCurves has grouped the 2 curves together as per the MUTCD and specified a sign at the start and end of the set of grouped curves. When I click on the southern sign, a pop-up describes the sign, i.e. a W1-4, that's in the right configuration. SafeCurves also describes why the sign is justified, so it provides an auditable process if there was ever a query as to why the sign exists and why it is a certain style. SafeCurves uses the MUTCD 11th edition that was published in December 2023 so it's up to date with the latest practice. Similarly, I can do exactly the same with the speed advisory, which recommends 60 mph speed plaque, and it also provides the justification for that sign too. I can use the same icon I previously used to go straight through to the Google Street View location. And here we are, but you'll see the sign is different to that specified by the MUTCD. The Google Street View shows that, at least in January of this year, there was a W1-2 sign installed, but MUTCD specifies a W1-4 sign, and it also recommends that that sign have an advisory speed plaque of 60 mph. Therefore, you might decide to substitute the W1-2 with the W1-4 and also choose to install the recommended speed advisory plaque because, as we know, this is a more risky curve because it's a class 1 curve. I tried to list some of the wider features and benefits of safe curves here, but simplistically, I think the key benefits of safe curves are that it provides insight on horizontal curve safety across your entire road network, regardless of scale. And I've already described why horizontal curve safety is an important issue to address. It also saves time and effort because it provides a far faster assessment method than traditional methods. And for the United States, we've already assessed all of the roads, all of the curves, their prioritization, and their MUTCD requirements. Okay, so we're nearing the end. What about next steps? If you're interested in safe curves and you'd like help in preparing your grant application that includes the purchase of safe curves, then please contact me. Once you have safe curves, you'll be able to develop a systemic roadway departure program, and the next time the TTPSF opens, you'll be able to apply for a grant to implement your systemic roadway departure countermeasures. Finally, this is my email address. To get the process started, ask me a question, or if you're looking for some more in-depth demo, just shoot me a note. Our team is keen to extend our international expertise and reach other jurisdictions. We really do want to make a measurable difference improving road safety. That's what drives us. Jamie, thanks very much again for the privilege of speaking. Back to you.
Thank you so much, Steve. And just a reminder for everyone, we will be taking questions at the very end of today's training. So if you do have any questions for Steve, please put those in the Q&A pod on the right-hand side. Our next presenter is going to be Larry Moore. Larry is an executive professional with over 30 years experience who has worked in a variety of industries and is consistently a member of the executive team. Business development has been his primary role, and he is committed to transactions that benefit both parties in any negotiation. Larry has a passion for innovative products that truly revolutionize the current practices and make a difference for individuals. Saving lives on our roadways is a priority.
Great.
Larry,
Thank you,
over
Jamie.
to you.
Yeah, thank you, Jamie. Well, welcome everybody, and glad you're attending. That was pretty helpful information that we just saw, and we take a slightly different approach to those challenges. So let me put this in full screen mode. And when we talk about what we're trying to accomplish, we're finding that using the actual measurements from the field to be our basis of how we do our analyses. So we have two different capacities that we do that. First is our 123bim.com platform, which we've been using since 2005. And what we're doing is creating visualizations, but we're also able to look at the geometric challenges or use for those for public involvement. Where I'm going to spend the bulk of my time today, though, is talking about our RSA 3D, which are 3D simulations and services. We're using a lot of AI and automation to identify potential safety deficiencies by actually using that 3D model. In our case, we use a LiDAR point cloud to do several different analyses, sight distance analysis, the geometric measurements of the roadway and the embankment, and even working in solar glare and how that may play into any kind of safety characteristics. But before we start, the Green Book has been around for a long time, and in a 2D context, we were using it to do these calculations. But really, the spirit of the Green Book guidelines are to ensure sight distance along the entire design or the corridor. It's not just about hitting the numbers, and the goal is to achieve sight distance. So as we think about this, what an elegant way to do this by putting it in a 3D context. So I'm going to play this video, and this is a point cloud from one of our customers. And the first thing we'll do is bring in that 3D model. And from there, we'll then digitize the road lanes. And then we start working our way through the environment in 10-foot intervals and asking the question, can I see the object that I'm supposed to be able to see? That red ball out there represents the 2-foot object for the stopping sight distance paradigm. And we look through the entire environment looking for that object and capture all of those measurements. So in essence, we're drawing sight lines through an entire corridor to understand where we can see and where we can't. Whoops. So the same application can be used for different paradigms. In this case, we're going to see intersection sight distance. This was in Pennsylvania. We're going to fly into this environment. They wanted 10-foot setbacks instead of the 14-foot that the Green Book calls for. So we put the driver's eye at that 10-foot setback, and we're now looking for that 3.5-foot object coming through the environment. And really, from a bird's eye perspective, here's what's happening. That very furthest point is where the sight triangle should start, but in the end, the object is not visible until you see the green aspects of that. So in a nutshell, roughly half of the sight triangle is not visible in this particular at this particular intersection. On this project, we actually did 45 intersections over a 5-mile corridor. It was a semi-urban, meaning there was a lot of residential. However, there was some commercial in here, and to be able to assess that in any kind of scalable way efficiently for 47 intersections manually was just almost impossible, or would take a tremendous amount of resources and time. Lastly, we can then use this exact same type of thinking on the passing sight distance paradigm. And you see us looking for that 3.5-foot object in the opposite lane. There are different methodologies to check the striping currently, but a lot of times what we're doing is taking 2 cars and following each other in the same lane using GPS. In this particular case, we're able to simulate it in the opposing lane and using all of the AASHTO Green Book calculations. Now, it's important to note here, any of those variables can be manipulated in our analyses. A lot of times we'll start with the Green Book tables as our starting point for whichever paradigm we're analyzing. However, we can plug in MUTCD, we can look at 85th percentile speeds, we can change the eye height. If you know there's a lot of tractor trailer traffic, for example, we can move that eye height from the typical 3.5-foot to, let's say, 6-foot. Really, because we're in this simulated sandbox here, we can change those variables, get you the results for 2 different approaches, and then you can look for the deltas in between. The point is that we're really trying to encourage the ability to measure and experiment with different real world scenarios. So in addition, we're taking that LiDAR point cloud and doing something similar to what we just watched. We're looking for the horizontal curves as well and doing a virtual ball bank using that LiDAR point cloud and all the measurements of the radius and those types of things. But in addition, we can look for pavement widths, shoulder widths, flat spot detection, which is essentially looking for that gradient calculation. We can do embankment characteristic studies. We're engaged with a state currently where they're asking themselves, does this embankment, is it recoverable or non-recoverable? If it's non-recoverable, do we have guardrail there? And we're employing a lot of AI. They gave us the exact slope counts that they wanted us to use, and we were then able to take that and analyze over 100 miles at scale as a starting point to say, here are the slope results, and there are several areas where you don't have guardrail. At that point, the DOT will then decide, should we do earthwork and make this a recoverable slope, or should we add that guardrail inventory? Similarly, another state that we're working with has asked us to do clear zone studies in this particular, using this type of analysis as well. So as you can see on the grid below in the picture here, we can actually look at that in a cross-sectional perspective and then start looking for things in that clear zone, the vegetation density, the slope and the height as well. So a lot can be done with that 3D environment, and we keep adding different things. Lastly, you'll see the solar glare here. We're doing that for some of our customers that are really trying to understand the environment and where they're seeing crashes at specific times in the day, wondering if solar glare is part of that. So we know where the driver's eye angle is. Obviously, we always know where the sun is relative to that, and then we can do the calculations. Much like Steve, you'll see in that table that below, we lat long everything so that you can go check Google Maps as well. So everything is tied back to latitude and longitude, and therefore we're able to pinpoint those locations that you can use other tool sets out there to maybe analyze the environment or verify or double check the environment from your desktop. So as we talk about that cross-sectional analysis, looking for those clear zone aspects or slopes, we can take that information, put it back in into our reporting system, but ultimately then you can get all the measurements out of that for your benefit in terms of trying to understand exactly what's happening in the environment and what safety countermeasures you might employ. One interesting thing is we partnered with Utah DOT and Michigan State University on an NCHRP study. Excuse me, and that NCHRP study actually created a safety performance function for stopping sight distance. First time it's ever really been quantified in this aspect, but that SPF factor of the more, is it more likely for a crash in a particular area? That's all out there. The QR code is here. You can actually go take a look at that. Dr. Pete Savalainen and his team, as well as UDOT, did a fantastic job, and we were honored to be part of that study. Pretty exciting stuff. We're moving on to intersection and passing zone aspects as well, and hoping shortly here that we'll have safety performance functions for those as well. Most recently, we've been working with KLJ and Adam on a particular segment in Montana. It's Montana 212 and is the North Cheyenne tribal area. I took a couple of these screenshots. This is literally hot off the press. We just got done. I just saw the results of the analysis today. So that top picture represents each dot represents 10-foot interval, and all the calculations that go with it you can see in the tabular report. But this visual, what it's illustrating is where the striping is currently allowing passing, and there isn't the sight distance available for the speed. So that's what that red area represents, is areas where what's in the existing condition does not match what the actual site distance characteristics are, okay? Likewise, the green represents areas that are currently striped for no passing. However, they meet the site distance criteria. If there's areas that you wanted to add passing zones for performance reasons, these might be good candidates. However, every state has a little different requirement in terms of how much length they want those to be. Are there other intersecting roads? There's other considerations, but it's a very quick and efficient way for you to be able to look at an environment and say, okay, first of all, where is our striping incorrect with the site distance available at this speed? And then the second question becomes, where could we put passing zones if we have to change some of the striping configuration where it doesn't match site distance? The bottom picture is the flat spots analysis from this segment. It was about a 40-mile long segment. And I just took a screenshot. These flat spots are the gradient calculation. And what's highlighted here is anything with a calculation under 1. Most of the time, as I talk to maintenance folks across this wonderful country, they already know where these are intuitively, particularly in areas that have winter considerations. These spots are where you're going to find your black ice to be more likely. They're going to be the areas where hydroplaning is much more prevalent, and those types of things. And so generally speaking, how this is being leveraged is when the rehab cycle comes up, they make sure that the contractor or the consultant that has been selected to help with that rehab project is aware of where some of these areas are, and they can make the corrections when they're milling and filling. So really a productive way, another aspect of safety to look at these roadways. Here are a couple video clips of there it goes. This is actually from the LiDAR point cloud. We're looking for the two-foot object on the left-hand side for stopping site distance. And that's actually from the 212 study that we just did. And then likewise, we have a passing zone aspect where we're looking for that 3.5-foot object out here at the correct distance. We're going at 65 miles an hour, and then use the tables to understand how well we can see it. I realize it's roughly 1,200 feet out there, so to see that 3.5-foot object is difficult unless we have a zoom feature that you can look at. But as we're looking at that MP4 video, you see the visibility percentage up there, and what that constitutes is the number of pixels that are part of that 3.5-foot object. Thankfully, the computer can see it and knows how visible it is. So anyway, but both just new examples of putting the technology to use. I alluded to earlier, kind of like the safe curves we were just talking about of doing a horizontal ball bank. This is one we did for Alabama, where we measured all of the horizontal curves along this corridor and then put it into a table format of where the super elevation is not matching and looking at that radius. So each one of these curves could be evaluated this way, and we're doing large segments and breaking it all down in this kind of context. Once again, though, you can change these variables. We can use whatever numbers and crowning and friction factors and those types of things that you want us that are applicable for your particular scenario. So from a deliverable standpoint, we have a summary of findings report that kind of gives the highlights. You didn't have time to watch the entire sporting event, but you did tune into ESPN to look at the highlights, and that's what that summary of findings report is, to help with prioritization, but also to call your attention to some of the biggest offenders in the environment. We deliver shapefiles so that you can put this in your GIS database and use other data sources such as crash data or other traffic volumes. You know, a lot of organizations have a lot of different GIS capabilities, and so this just becomes another data point that they can compare with some of the other data they have. We can output CAD files when we do the same kind of analyses on proposed designs. It also has a CSV file. If you're a person that really doesn't like GIS that much, but want all the hard data numbers, the CSV file will have all of that. And then we have our online interactive reports, as well as we create an MP4 video of every simulation that we do, whether it's intersection, passing zone, stopping, sight distance. All of them have their own MP4 videos. From a proposed design standpoint, you can see here, we're measuring in 10-foot intervals this 3D environment that was created and looking at the maximum speed. So this is the stopping sight distance calculations on this entire corridor. So you can look very quickly here. You could click that on that QR code and take a look at that in more detail. With only 15 minutes here, I realize I'm moving fairly fast, but wanted to at least give you an overview of that. So as I wrap up, here is my contact information. And as Jamie mentioned, we'll have Q&A at the end, but please let me know or drop me a line if you'd like more details or to see some other examples. We've worked in several states and several municipalities with this kind of technology, and we can talk through some of how it's being leveraged. So Jamie, with that, I'll turn it back to you. Thank you.
Perfect. Thank you so much, Larry. And for everyone joining us again, if you have questions, please put those in the Q&A pod over on the right-hand side. Additionally, in the chat pod, I have started dropping the contact information for our previous speakers. I'll put Larry's in there right after I introduce our next speaker. So our next speaker is going to be Zach Hans. Zach is the director of the Center for Weather Impacts on Mobility and Safety and a research and development engineer at the Institute for Transportation, or INTRANS, at Iowa State University. Zach has more than 29 years of professional experience in transportation engineering, working in the areas of traffic safety, operations, planning, maintenance, and enforcement. Zach has supported the United States Road Assessment, or USRAP, since its inception in 2004. And I'm excited to turn over the program to Zach.
All right, thank you, Jamie. Can you see the full screen here?
We can, yes.
All right, thank you. So I want to take a little time today to talk about USRAP, as Jamie said. USRAP essentially is a software tool that assists highway agencies in selecting or identifying infrastructure projects that will improve the safety of their network. It is currently housed at Roadway Safety Foundation, supported through Federal Highway Administration, and it focuses on reducing the risks of fatal and serious injury crashes across the network, and then also ensures that that any kind of investments that are made, particularly for road safety improvements, are based on kind of a rational assessment of the risk. USRAP is a systemic approach. As Adam talked about, it looks at proactively improving the network that has the highest potential for crash reduction. You don't have to wait for crashes to happen. It looks at the network as a whole. It focuses on the long-term improvement needs and not simply kind of the traditional hotspot analysis where you're looking at maybe short-term crash patterns. So this provides a benefit of again, being proactive and systemic in assessing where your needs are and what kind of countermeasures can be applied. This is a general schematic of the USRAP analysis process. It typically begins with images of the roadway data that can be coded for different roadway characteristics. Other data sets can be used as well that would be available that would fit those needs. The data is then prepared, and then this is the next three components are the VITA software, or within VITA software. It processes the data, it creates star ratings, which I'll discuss what the star ratings are. It creates a safer road investment plan. So based on the data that's being observed, roadway characteristics, and a set of countermeasures, where are the best locations to invest funding? Then an output of this or considering the output of the Safer Road Investment Plan would be considering engineering studies for these recommendations. These are recommendations that traditional engineering studies can then assess and then ultimately develop an implementation plan for the safety improvements that are viewed to have the greatest improvement throughout the network. You'll see some common themes throughout this. I might repeat a few times, but I wanted to kind of give an overview of VITA and the star rating process, as well as the Safer Road Investment Plan. So you will see some common themes throughout. But regarding the VITA software, it allows the upload of this coded roadway data. It processes that data. It will display the data on screen. The output of the data can be downloaded, of the results can be downloaded. A key element is it does not require site-specific crash data. So if an agency does not have great crash data, great locations of crash data, general network-wide data is useful simply for calibration of the model to those local conditions. So just in general, knowing where how many fatal and serious injury crashes have occurred throughout the roadway network that's being assessed can be utilized in VIDA. The VIDA software itself and technical support, which is provided by Roadway Safety Foundation, are both free of charge. I've provided a link here, and it will be provided in the handout material for how to sign up for a VIDA account. Anyone can sign up for a free VIDA account. There's certain capabilities you'll be able to see in VIDA, and I'll touch on a few of those. Otherwise, any local agency or specific agency data, access to that is managed, but otherwise just kind of general VIDA access is open to anybody to log in and sign up for. Kind of getting to that local level, thinking about how VIDA software can be applied, it does allow for local situations. So you can modify the countermeasure unit costs, which countermeasures you want to consider in analysis, what the countermeasure service life may be, what your agency considers the cost or the economic loss, societal cost of fatality or serious injury, also the minimum benefit cost ratio to consider in analysis. If you wanted to see any kind of benefit that would result of a benefit cost ratio of 1 to 0, if you want to look at what does the network look like if we go to 2 or 3, a benefit cost ratio, you have the opportunity to modify those as well. So ultimately, the software, VIDA software, will provide estimates of the fatality and serious injuries throughout this road network. The road network is coded at 100-meter intervals. It will provide star ratings for that network and tables, maps, and files that you can download and display in your own GIS. It will provide a safer road investment plan, as I said. That information is tabular maps, again, in download files. It'll show that if you make that investment in that plan as proposed based on whatever benefit cost ratio that you define, where you're going to see the reduction in fatalities and serious injuries throughout your network. And then also you can download those countermeasures that have been identified as being the ones that would reduce crash risk the most. These are going to include the locations, the specific benefits, and the costs of those improvements, and then the benefit cost ratio of those improvements at all the sites throughout that have been identified. So kind of transitioning into the next step, into thinking about how that star ratings are defined in the VIDA software. They're really based on the presence or absence of different roadway characteristics and traffic control features, traffic flow, the network. There's over 40, or there are over 50 that are defined at the roadway level at 100-meter segments, as I said. Really, the star ratings are the first step to considering the safety performance of the roadway. So much like it's star ratings for vehicles, there are star ratings for roads. So a 1-star is has the fewest safety features, and a 5-star road has the most safety features. Speed does have a great impact on that. So a benefit of the star rating is you can also see how different roadway characteristics have an impact on safety, and that I will touch on that is through a demonstrator aspect within the VIDA software. As I mentioned, star ratings are on a 1 to 5 scale, and star ratings are provided for different user groups. So for vehicle occupants, for motorcyclists or other motorized two-wheelers, for vulnerable road users as PEDs and bikes as well, we have different star ratings for each one of those user types throughout your network. And this is an example of just a screenshot of the demonstrator software. It will show how you have, for these different star ratings in different user groups, how different roadway, mid-block, intersection flow, facilities for vulnerable road users, and land use, and then speed data, the 85th percentile speed, the regulatory speed, how those impact the star rating. So you can go in, I've picked here in this example, a low standard. They have several different standard road sections set up, but you can go in and pick one and then make changes in each one of the attributes. So in this case is an example of looking at, this is more kind of a pictograph version, looking at on the driver's side, there's a tree within 1 to 5 meters of the roadway. There's a tree on the passenger side, 1 to 5 meters. That section of roadway does not have rumble strips. There's no paved shoulders. It's an undivided roadway. Cost to improve that roadway, maybe to add lanes or clear out some of the, maybe expand the clear zone, would be low. There's center line only, there's no center line rumble strips, etc. So you can go in and make changes to each one of these and see how that affects the score for each one of the user types of the network. This provides just kind of another example of that, but more of a drop-down list. So you can see, okay, we're looking at the severity of how close is the severe object to each side of the roadway, what type of object, again, shoulder presence, and are there shoulder rumble strips? And you can go through each one of these. And if we have time, I can provide a demonstration. Otherwise, each person can sign up and go through this themselves and see how different features of the roadway, roadside, flow characteristics, traffic volumes, and speeds will impact star rating for the different users of the network. And kind of really key element of this is getting to this investment plan, kind of thinking about that risk component based on what characteristics exist in the network, how you can improve your network and reduce the fatal and serious injury crashes. So the investment plan, it identifies, again, those specific improvements at specific locations throughout the network based on the characteristics that exist currently in the network. And then it provides an estimated cost and benefits for each one of those countermeasures that have been selected based on the parameters that you defined, the maximum or minimum benefit cost ratio, the cost that you have for estimates for each one of the type of countermeasures being considered. The investment plans, again, are based on these roadway characteristics and roadside characteristics and flow characteristics that have been coded at 100-meter segments. There are more than 90 different countermeasures that are considered and over 300 different engineering trigger sets for consideration for these different countermeasures at different locations throughout the roadway network. Anyone can really benefit from use of a Safer Road Investment Plan because it helps you prioritize where these infrastructure improvements can best improve safety, reduce your fatal and serious injury crashes. And again, without very detailed crash data, just broad crash data for the network that you're analyzing as a whole. So what the user will get out of a Safer Road Investment Plan will be where sites can be improved, what type of countermeasures can be applied, and there can be multiple countermeasures at individual locations, the cost of those countermeasures, what the anticipated benefits are, specifically with respect to savings in fatalities and serious injuries. And again, that kind of goes back to some of those cost estimates that you provided for societal costs for those type of injuries. And then ultimately, this information then can be used to implement kind of these more traditional site-specific engineering studies. So this is a planning level assessment suggesting locations where improvements may be beneficial that then can go into more detailed analysis to define what your implementation plan will be. Overall, as I touched on, USRAP can be applied for any roadway network. In any roadway, you can look at a single roadway, you can look at multiple roadways in the network. It does not replace engineering judgment and local expertise. There's a lot of areas where you can provide some of that local expertise with respect to what your anticipated peak hour flows are for peds and bikes, what your traffic volumes are, any kind of countermeasure costs, because those can change from different locations in the country. It's a planning tool, it's not a design tool. So keep that in mind as it's part of the process to develop an implementation, actual implementation plan for safety improvements. It identifies cost-effective projects quickly based on your network and what kind of characteristics exist in the network. It's really potentially beneficial for locations without good crash data, without comprehensive crash data or site-specific crash data. And also networks, a lot of these rural networks have very low traffic volumes. You're gonna have fatal and severe crashes, but they're gonna be spread throughout the network. So looking at this risk-based systemic approach, you're gonna make improvements, target improvements on your network where you have the highest risk and a potential for these severe crashes. FHWA has identified it as a data-driven safety approach, and it allows agencies to take actions now instead of waiting for crashes to happen. The traditional hotspot analysis where you're looking at sites where multiple crashes have happened. But again, on these low volume networks, and even on higher volume networks, a lot of these serious crashes are kind of distributed throughout, and it's hard to target where you make these improvements. There's some training material that's free online. There's a link here. There's two main training materials. One is kind of a longer version of this presentation talking about USRAP as a whole, the process of doing a USRAP study. The second one is an actual complete course on data preparation. So that step in the process of collecting the data for the network and then uploading it to VITA. And then we can provide through a Roadway Safety Foundation some more detailed support for actually utilizing the VITA software. Contacts would be FHWA, as well as Bruce Hamilton, who is the Executive Director at the Roadway Safety Foundation. So I'm going to, if I have a minute, I can show you quickly the demonstrator. Can you tell me, Jamie, can you see the demonstrator?
I can see it, yes.
All right, so thank you. So this, I had given a couple slides here. So this gives a typical roadway section. So for example, if I made a simple change and say, change this from a centerline rumble strips not present to a centerline rumble strip present, you'll be able to see some changes throughout the network. You'll see that it will give you warnings that it's unlikely if the delineation is considered poor. So for example, delineation is one consideration. So as you go through, it will ask you, okay, consider my delineation adequate. And so now you can still see on this cross section of roadway, you did have a numerical increase or decrease in the risk, but you still were in that 1-star range. If you go in and make some other changes, for example, the distance to trees might be over 30 feet away, we can see what the results are. And now, just simply making that clear zone wider, you've increased the star rating from a 1-star to a 2-star, from in the 60s to 70s to a 17, and then also increased other users. You'll notice here that we do not have star ratings for the pedestrians and bicyclists. This is simply because we're looking at a rural environment. If we change that to an urban environment, we'd be able to see that we'd get, if we look at a low standard urban environment, for example, it's going to show us, based on those characteristics for that environment, what the star ratings are for the vehicle occupants, motorcyclists, bikes, and peds. We'd want to go in and look at those various characteristics to see what exists on those networks. And it talks about expected flow, if there's bike facilities or not, what the land use is. There's no bike lanes, for example, and no sidewalks, which would say why this is a low star rating and a high score for risk. But this allows users to go in, even without collecting the data, to be able to get a feel for how different characteristics across the network do impact safety. And you can change the speed limit, what you anticipate to be the 85th percentile speed, or if you have speed studies, utilize that as well. So I appreciate the time, Jamie, and I will answer any questions at the end of the presentation.
Perfect, thank you so much. And once again, you can put questions in that Q&A pod over on the right-hand side. I will remind you that there is a handout pod also on the right-hand side where you can download all of these presentations. A lot of the presentations have gone through links of things that are available, and you'll be able to see those in the PDFs that are available in that handout pod. Now, our next presentation is going to have two different speakers. I'm going to read you the bio for the second speaker first, and then we'll go backwards to the one that I'm about to hand it off to. So our second speaker in this last part is going to be Shahrejad Hassan, who is an Associate Research Fellow at North Dakota State University's Upper Great Plains Transportation Institute. Specializing in intelligent transportation systems, he primarily focuses on systems engineering maintenance and integration of advanced technologies to enhance transportation infrastructure and safety. He is actively involved in the roadway and pavement coding for the Crow and Northern Cheyenne tribe by developing a comprehensive guide tailored to the tribal areas. Currently, he is exploring innovative approaches with artificial intelligence in road safety assessment coding, all while adhering to the USRAP guidelines that we just heard about. So our first speaker for this next session, who I'm about to hand this over to, is Ronald Hall. He is an enrolled member of the 3 affiliated tribes and the Tribal Transportation Program Manager for the Upper Great Plains Transportation Institute. At UGPTI, he is the co-director of the Northern Tribal Technical Assistance Program, serving tribes in North Dakota, South Dakota, Nebraska, Wyoming, and Montana. He is also assistant director for the tribal transportation programs in the Center for Transformative Infrastructure Preservation and Sustainability. Mr. Hall is a lawyer who works nationally to understand and support the research, capacity building, technology transfer, and strategic planning needs of tribal transportation programs. And I'm happy to hand our presentation over now to Ron. Ron?
Great, thank you, Jamie. Thank you, everybody, for joining us to talk about this really important topic. Today, I'll be sharing what we're working on with the Crow Tribe and Northern Cheyenne Tribe in Montana. And really, we had a safety peer exchange back in August last year that helped us kind of bring attention to the dire kind of stats that are out there for Montana with the runoff road crash issues. And fortunately, that peer exchange kind of led to the discussion of doing a further work and working with Adam Larson using GoPro cameras and some really usable technology that tribes could implement on a local level, and applying some of the other more advanced tools on top of that. So that's what we our goal at the beginning was to develop end up with a systemic runoff road analysis and plan that the tribes could both use to turn into safety proposals and action to correct these issues. So if you go ahead to the next slide. Thank you. And just also to mention some of the issues in Montana. In 2020, they had 20,000 crashes statewide, 189 fatal crashes, and 212 fatalities. Over a 10-year average, they had roughly 202 fatalities per year. So the runoff road crashes are 63% of those, and the 63% of those were on rural roads. So that kind of leading, most of the travel roads on the reservation are rural in character and volume and all the criteria. The tribal share of those crash fatalities was alarming. Represented 18% of all the fatal crashes. Well, Native American people are 7% of the population in Montana, so way overrepresented in the fatals. And we also had an issue with a data desert, as Adam described earlier, that we had crash data on the state system, but the BIA system it was not accessible. So we needed another way to determine safety needs and issues on the off-state system as well. And also, we had significant crashes on the state system and needed to do some analysis there as well. So the pilot project that we're working on, our focus is to work with the local crew in the travel road department. They are the eyes, ears. They're the ones who are going to be working on this issue. So I will say that when we're talking about the BIA road system out in tribal lands, there's nobody else whose job it is, who has resources to do anything about it with regard to safety and crash reduction, except the tribe. And so if the tribe doesn't do anything about it, nothing's going to happen. And so the impetus of this project is to work with the local staff, train them on how to use the cameras, and manage the data at the local level, and then get it uploaded up so that we could process it at North Dakota State University. And so that was basically kind of the big scale workflow. Adam helped us with some processing on the first stage to get it up into the Google Street View and Mapillary platforms, and then the data was shared with us. What our crew and Sherjad will go into more detail about the coding and how we worked with the data once we got it, but and to then tie into the VITA software package that was just described. Next slide, please. So this is, we had some paper maps that we started with to help identify what, left it to the tribe to decide what the priority routes were to go out and do the video data collection. And we were able to record those and then get them into the GIS and show where the progress was. And we had to do it in a couple of different phases. We had some, weather caught us a couple of times. We had some issues with vegetation, some issues. The camera lens was, bugs or something got on it. I had to go redo things. It took a few iterations to get out and get the data collected. Next slide, please. And this is basically the process. We had the camera, 360-degree camera, 2 lenses, so it amazing the quality of the imagery that it can collect. It also has a GPS internal, and I believe it would also get an elevation. So at least of the point of the camera. Otherwise, the imagery itself is flat. We don't have LiDAR type data that we can do real spatial analysis with, but it does capture a center line, and it does capture, I believe, an elevation of the camera. And it gets mounted on the top of the vehicle. Keeping it mounted is sometimes an issue, depending if your vehicle is aluminum. We need another way to make, you can't use a magnet. We learned those lessons, and we're able to get the data collected. And so with the 360, you just drive one direction, and it collects both the front and the back view. So I think, Sherjad, I'll turn it over to you to talk about what we did after we got the imagery.
Sure. Thank you, Ron, and thanks, Jamie, for the introduction. Can you see the full screen presentation?
Yes. Looks
okay,
great.
Perfect. So as Ron just mentioned, that we collect the images from those 360-degree cameras, and Adam helped us putting it into those images to Google and Mapillary. Because why we have uploaded those images to Google? Because we need to bring those images to the coder so that they can code those road sections, and the coders need to have it in a systematic manner. Now, uploading these images to the online mapping services like the Google Street View on the left, or another service like Mapillary, that helps a lot in this case. Each platform has its own perks. Like Google has a wide vision mode where you can move into different timeline of images. So you can move from 2023 images to 2015 images if it is available. And whereas the Mapillary, that has a very active image scrolling option. So when the coders are coding, they can quickly move forward or backward on those images. However, both systems use the coordinate based mapping to stitch those images, and we actually leverage that system on ArcGIS. So what we did is on the ArcGIS road network, we created the points for every 100 meter, and based on that, we attach those images or those images between each 100 meter points. And these will lead to what we want to do for the with those images. Once we have those images, what does the coders do? They look into those road sections to complete a USRAP provided pre-processing tool, and they use that inventory system to code for every 100 meter of a road section, as Zach already mentioned. And to work with VIDA, there are total 78 attributes that needs to be identified for each road section. And in the tool, we can only see the option of completing 64 attributes out of 78. And again, out of those 64 attributes, 16 are taken care of during the either the pre-processing or the post-processing. For example, the coder name or the image section, etc. And other data types like the intersection attributes or the pavement condition, those have been taken care of by the coder during the coding period. Now, to increase the accuracy in the data coding, a few roadway attributes may be coded in a different format. In some studies, the USRAP team leader can code some roadway attributes that are unlikely to change. So, for example, the observed motorcycle flow, or the speed limit, or the truck speed limit, they are kind of similar for the whole road section. The post-coding attributes are also being used. They're generally added to the data file after the data coding is completed by a coder. And the post-coding stage, it also provides an opportunity for the team leader to review and make needed correction to the coded data. Now, this is what a coder actually looks when they code for the data. So on the right side, you are seeing the pre-processing tool that I'm talking about. You've probably been not be able to read the each of these words or each of the attribute definition. However, they look into the image or the set of images for the whole 100 meter, and based on that, they they fill up all these 64 images. And once they fill it up, they can actually hold each of these boxes and they can carry those information for the next 100 meter. So in that way, they do not actually have to change each and every attribute item for the roadway sections coding. Now, once the coding part is done, we go for the validation for of those coded data, and eventually the data will be ready for to be used by the VIDA star rating. Meanwhile, depending on what is the project scope, we brought the second solution, we brought another solution towards the data desert, which is for the tribal areas to check whether the ratings are reasonable for the tribal areas. Now, that solution is we have used the FARS, or the Fatality Analysis Reporting System, which is actually a nationwide database for the motor vehicle fatalities. It helps us to identify the trends of fatal accidents, as you can see on the image from the which goes between the year 2018 to 2022, and also it helps us to figure out whether the traffic-related deaths whether we can reach the goal of reducing these traffic-related deaths by mapping it on our on the ArcGIS or on our total road network. So as you can see, we have what we did is we identified all the fatal crashes on the ArcGIS, and because of our project goal is developing safety implementation plan against roadway departure, we have identified those separately from the FARS data. So I just zoomed it in a little bit so that you can see that we identified those rollover or overturn type of data, and it came out that only in the Crow Reservation area there are total 30 roadway departure crashes out of 43 of total crashes, whereas for the whole Crow and the Northern Cheyenne area it's 40 roadway departure crashes out of 63. Now, using this crash data, we can map all those crashes in the total network, and based on what our coders have been coded, and from the code how the star ratings have been generated, those can be compiled into one map and to see whether the location of these fatal crashes actually makes sense to for the engineering study or not. And that's pretty much the biggest purpose of considering these FARS data and calibrating this network. So, and this part I'll skip a little bit because Zach already has mentioned these one that based on this coding, based on the road coding, a road safety score will be determined, which will then again assign a star rating that Zach already showed. And it will look probably similar to these images on the right side of the screen. And these star ratings are based on how the coders actually read the road, or the presence and presence or absence of any design elements or traffic control features, and also traffic volume and the speed, and if there is crash data available for the whole network level calibration. And that will take eventually that will take the tribe to the safer road investment plan, which again Zach has already presented in front of you, and VIDA will assess each of these road section for 70 specific countermeasures, I believe, and because it deals with the data from every 100-meter section, it can actually assign those measures for a specific length and location. And it will also perform a benefit cost analysis for every countermeasures for which a need is identified, as well as the analysis for the whole network will also be provided. Now, this is how we, this is kind of, you can think it as a connecting point of how the road, how the images taken from the road can go all the way up to the VIDA. And there are some other users we have seen or we have that has been reported of the 360 camera. For example, the Cherokee Nation, they use the 360 camera before each project to document the conditions. An example they gave us is it was useful to address the citizen complaints about a mailbox being removed but not replaced during the construction. Also, it can be used to facilitate the size up maintenance, to size up the maintenance projects so that the appropriate materials can be gathered before mobilizing for a repair, or even monitoring the contractor progress and project details. So if you have any more questions about our project, here is our contact details. And with that, we will move to the question and answer sections.
Perfect. Thank you so much. And just a reminder that those the Q&A pod can be used for questions over on the right-hand side of the screen. If you do have any, please go ahead and put those in there. I'm also going to put up on the screen right now the contact information for all of our speakers in case you have any questions after we finish today's webinar. So we did have one question come in, and I believe it's for Zach, and that is, can the VIDA software analyze existing MP4 video footage?
I think the data are coded at 100 meter, 327 foot intervals. So whatever, if there's an approach established to be able to record the necessary attributes based on that MP4, it can be used. Many people have used different video log techniques. I know we've talked about using Google Street View. So there are possibilities as long, excuse me, as there's confidence that you're able to report the characteristics at that predefined intervals.
Perfect. Thank you so much. And that actually was our only question that we have. So I'm going to go through a few last things. If you do have any final questions, please get those entered into the Q&A pod on the right-hand side. I do want to remind everyone that the PDFs of our presentations today are available for download in the handout pod on the right-hand side of your screen. Additionally, in the chat pod, I have put all the contact information that you're seeing in front of you right now as well. And then a reminder that a recording of today's webinar will be available within the next few days on the Rural Safety Center's website, which I also put in the chat pod. I do see that someone has raised their hand. Unfortunately, we're not able to unmute phone lines. So if you do have a question, please put that in the Q&A pod as we finish up here. Additionally, I do want to just thank all of our speakers one more time on behalf of the National Center for Rural Road Safety, the FHWA Office of Tribal Transportation, and the NLTAPA Safety Working Group. So thank you to Adam, Steve, Larry, Zach, Ron, Sharahead, and Kim. Thank you so much for presenting today. We truly appreciate it, and everyone have a great day.
Thanks, Jamie.
Thank you, Jamie.
Thanks, Jamie.
Thank you.